Swayam Prabha. Digital India. Educated India.
In this lecture, we'll be discussing the typical controls we use in the classical control synthesis. We'll start with proportional control, and we'll see the response of the aircraft system with the proportional control will be oscillatory around the equilibrium point. To avoid this problem, we'll take the help of derivative control, which will add basically damping to the system, and due to which the oscillation in the proportional control can be avoided. And then we'll move to PID control, where we'll be adding the integral part to the control. Basically, if there are disturbance acting in the system, and due to that disturbance, there is a steady state error in the response. And through the help of integral control, that steady state error can be mitigated over time. Then we'll conclude the lecture. In this lecture, we'll be discussing what are the typical control algorithm we use in classical domain, classical control system domain. Let's redraw the figure we had in the previous lecture, the closed loop diagram. So we had our reference value. This is, we can write R of t. And we had controller. This is GC of S. And the output from the GC of S, we had U of S, you can write, or you can write R of S, the reference signal. And this control, before it goes to the system, we had also the disturbance, MDS, and the summed output was going to the plant. So GP of S, this is output, Y of S. In the feedback, we had measurement noise, which is due to the sensor malfunction maybe. And this was measurement noise, WS. And we had sensor transfer function, H of S. And the sensor generally we use to determine or detect the position or attitude of the aircraft. So this is how we had, and we assume H is a unity feedback system. So H is we used equal to 1. And in this lecture, we'll be discussing how we can come up with defined control algorithm in the controller block so that our mission objective is fulfilled. So we'll be designing defined controls in the controller and how we can fulfill our objective. So let me write the heading, typical control laws, typical controls we use in classical control techniques. We'll restrict ourselves not to consider the measurement noise. So we shall not consider the measurement noise for the time being. Omega is equal to 0. In this assumption, the motion of the attitude motion attitude motion of the aircraft, we can write I y double dot t equal to E of t plus the disturbance. So our motivation is how we can design a control algorithm in place of ut so that we can get the desired response y of t. Suppose our desired response is y dt, and how we can design control so that I can track yt to ydt. So yd can be a reference signal. This is my y of t, or it's maybe theta dt. So this is theta actual. So our objective is how we can make theta of t to theta dz t. So first, let's consider the proportional control. Proportional control. In proportional control, basically, it is just the scaling of the error signal. In proportional control, the control input is just a scaling of the error signal. So it means here we have error signal E of S, which is basically negative and positive. And this is my controller. This is the controller. And in controller, basically, this is we have to assume some kind of constant, which is scale the error signal so that we can get U of S. So let me write U of t. What we can write the output of the control block. We can write Kp E of t. So Kp is the scaling factor of the error signal, where Kp is greater than 0 is the proportional gain. And the associated transfer function, for the controller, we can write U of S is the output of the control block and Kp E of S. So output by input equal to transfer function, Laplace transform output divided by Laplace transform of input, basically transfer function. So U of S, E of S equal to Kp. This is Gc of S, and this is the controller transfer function. So now let's assume the reference signal which needs to be tracked yd. So here let's assume the reference signal r of t or y dt is constant. So if it is the reference signal is constant, it is kind of a regulator that we already discussed. And also since we'll be finding the transfer function of the entire system, and our main motivation is in this block how we can design the control so that ys can track rs. And since we need to find the transfer function between the input and output, this is my reference signal to the block, and this is the output from the block. So rs can be your input to the entire block here. So we need to find the a relation between RS and YS. So we'll not assume the disturbance or noise. So this is the actually main transfer function in the system. So we'll neglect also we neglect the disturbance term MDT. And based on this assumption, we can write our system attitude aircraft attitude motion. We can write IY double dot equal to E of t, because we are not assuming the disturbance. So E of t, what you have considered? K E of t. So we can write Kp E of t. And this equation further we can write Kp into E of t. We can write R of t minus Y of t. So here R is constant, we can just write R. Simply we can write R. And taking the Laplace transform, else we can write I s square y of s equal to Kp R of s minus Kp y of s. So here we have assumed initial condition on a condition will be 0. So this is the assumption for the finding the transfer function that we already discussed. And from this further we can write I s square plus Kp ys. We can take this equation, this term to left hand side. So we'll have this term in the left hand side equal to Kp into Rs. So from this we can write Ys divided by Rs equal to Kp plus I s squared plus Kp. So this is how we can write the transfer function, closed loop transfer function for this particular system. So this is my reference signal R of S, and this is the controller Kp. This is E of S, and this is the plant Cp of S, which is nothing but 1 upon I s square, and this is the Y of S, and this is basically feedback loop. So feedback. If you want to apply the direct expression, what you have done before, we know Ys by Rs. If you can remember, we had Gp of S, Gc of S divided by 1 plus Gp of S, Gc of S. This is the closed loop transfer function which relates between the output and input. So if you substitute the term Gp of S 1 upon I s square into Gc is Kp divided by 1 plus 1 by I s square into Kp. So if you solve this expression, you'll get Kp 1 upon, Kp by I s square plus Kp. The same expression we are getting. So if you want to use if you can remember this this expression, you can find the transfer function also. So this is our transfer function for this system using PI control. So I can say this is P control, proportional controlled closed loop aircraft attitude control system. So now we'll, as you discuss this, the denominator of the closed loop transfer function talks about the number of poles in the system, and numerator talks the number of zeros in the system. In the closed loop transfer function, that is very important. So pole and zero we can come up from any transfer function. This is closed loop transfer function, and this is the poles, this is the zeros. If it is open loop transfer function, for example, suppose we have open loop transfer function here. This is open loop transfer function. This is open loop transfer function. So here also we can come up with the poles and zeros. The numerator will be poles, denominator will be zeros. This is the open loop transfer. This is, I should not say open loop transfer function. This is the plant transfer function. Open loop transfer function we'll discuss later. What is open loop and closed loop? So this is the poles. So poles from this closed loop transfer function, basically the roots of the characteristic equation of the denominator. Basically, this is the characteristic equation or the polynomial in the denominator part. The result, if you find the, so from the characteristic equation, okay, maybe I have not discussed about it. Characteristic equation, basically the characteristic equation generally we write 1 plus GP of S, GC of S equal to 0. So in the closed loop transfer function, this part we call characteristic equation. This part 1 plus GP of S plus GC of S equal to 0. So now from this expression, we can get the characteristic equation I s squared plus kp equal to 0. And further we can write s squared equal to minus kp by I, and s equal to s1, that is 2 poles in the system. So we can, in the closed loop system, we can write plus minus I root over kp by I. So from these poles, it is clear that the system will be oscillatory. Why? Because the solution will be in the terms of sine and cosine. So if you place in our real and imaginary axis these poles, as I said before, S basically we can write sigma plus j omega. So who is this? This is the real part and this is the imaginary part. So in this case, we are having only the imaginary part, and in the S plane, this is basically S plane we call, and this is the real axis and this is the imaginary axis. I can say imaginary of S, this is the real of S. So since we are having only imaginary poles, so we are having 2 poles, one is here and one is here. Right, we can say this is root over kp by I, and this is minus root over kp by I in the imaginary axis. So now, if you see the response of the system response will be something. This is, or I can say, if you see the in time domain y of t and t, if you see the time domain, the response will be something like this. So it will be oscillatory without decay in the response. So what is the takeaway from this example? If you use PD proportional control in our control block, the response will be oscillatory behavior. Response is oscillatory. And if you connect to aircraft system, what is actually practically happening? This is the, let me draw this figure. It will give you some practical implication of this concept. So this is the line my aircraft would like to follow, for example. And let's assume this is the aircraft, for example. So this is the aircraft x-axis, for example, and this is my desired signal R, and so aircraft should follow this line, this line, this line. But so here, about this line, the aircraft will be oscillate. So suppose this is my spring, and spring constant is Kp, and this is the error. This is the error. So this is the actual value of y of t. So it means aircraft will oscillate about the reference line r, and with the oscillation omega root over kp by I. So this is practically happening. So this is basically this aircraft will not come to the reference line forever because of the nature of the system response. This response, the aircraft will be oscillate about the reference line. This is actually what will happen. So now, if you draw the closed loop diagram, in this case, so we are having, this is my R, this is the error, this is the control block, KP, and this is output UT, this is the plant, 1 upon IS square, this is Y of T, so this is the negative feedback. So this is the structure of the P controlled attitude system. So this is the P controlled attitude system, and this is the problem. So from this kind of response, we can say P controlled system is just a mass spring system. So if you connect to this kind of concept to mass spring system, it is the same kind of response you'll be getting, because the mass spring damper system, what is that expression? We know mx double dot plus bx dot plus kx equal to 0. So bx not exist here. So here we are having this kind of response. If you solve this equation, we'll get exactly same kind of response. So it is similar to mass spring system. So it means from the behavior, from the response, undamped oscillatory attitude motion of the aircraft will be there. So this is the problem in if you spring for this particular attitude control system of the aircraft. Now, to solve this problem, to resolve these issues, we need to consider another term which is called damper in the system. So in PD control system, we'll put a derivative term to compensate this kind of sustained oscillation behavior in the system. Now let's look how the derivative control look like. So the problem of sustained oscillation in P control system. P means proportional control system is not desirable. For this, we're gonna add proportional plus derivative or PD control to consider. So here the PD control law given by E of t equal to Kp. This is the part of the proportional control. So Kp is scaling factor and derivative control Kd E dot. So here we are adding the derivative of error to the proportional control. And here Kd is the derivative gain. Now we'll find the transfer function for the controller law. So the controller transfer function, the controller transfer function, we can write, if you take the Laplace transform of this equation, we can write U of S equal to Kp E of S plus Kd is E of S. And from this, we can write U of S divided by E of S plus KdS. So how the sustained oscillation can damped out using the PD control? Let's look. So this is my reference attitude. This is the reference attitude the aircraft should follow. Let's assume this is R of t or theta dt or y dt, same thing. The notation just changed. And this is the aircraft system. And this is the actual value output y of t. And in proportional control, we have spring here. And derivative control, we are damping. We are adding a damping term in this expression. So due to the damping, the oscillation, which is due to the spring, can die out. So this is the error. So error will initially, it may have some oscillation, but after some time, due to this damping term, it will go out. So let's look how it is happening. Similar to the previous control here, let's assume R of t is a constant reference attitude to be tracked. And similar to neglecting the disturbance in the equation, the aircraft equation of motion, of attitude motion yields to be I y double dot equal to Kp E plus Kd E dot. Since we are assuming R to be constant, we can write further Kp R minus y of t plus Kd into R dot y of t. So here R is constant we are assuming. So we can write Kp R minus y of t minus Kd y of t. So this is the expression we are getting. And further we can write I y double dot plus Kd y dot plus Kp y equal to Kpr. And if you take Laplace transform, taking Laplace transform, we have I s square y of s plus kds y of s plus kp y of s equal to kp r of s. And further we can write y of s divided by r of s equal to kp divided by I s square plus kds plus kp. Or we can write kp divided by I. If we take I common from the denominator part, so we can write s square plus kdi into s plus kp divided by I. So this is the closed loop transfer function. This is closed loop transfer function of the PD controlled attitude motion of the aircraft. So now let's look how this the oscillation is going to be damped out. And as we said, this is the characteristic polynomial. This is the characteristic polynomial which gives us the pole, number of poles in the closed loop transfer function. So let's write the characteristic equation. We can write s squared plus kd divided by is plus kp by I equal to 0. From this we can write, so this is the second order system, we have two poles. We can write minus kd by I plus minus root over kd by I minus 4 into kp by I divided by 2. So this is the number of poles in the system. So now if you see these poles location in S domain, so this is maybe somewhere here. So there are two poles are somewhere here. So based on the values, even if the value, this part comes out to be imaginary, somewhere maybe here or here. But the real part is negative. So due to this, if you solve this equation, we'll have exponential term in the solution. So the system may start maybe like oscillation, but after some time it will damp out. So this is why it is damping out, because of the damp part in the system and because of the negative term in the poles. This is how we can modify the response what you had in the proportional control. Well, let's stop it here. In the next lecture, we'll be discussing how we can design PID control and how the disturbance in the system can be considered, and how due to the disturbance, how we can modify the controlled response. Thank you very much.